There. Oh, it's time. Oh, looks like I'm live already and didn't even realize it. Okay, this is Dr. V, and welcome Thursday night. And good to be here. Good to be here with each and every one of you. Um, Check in on the chat there. Let me know who's here. Always interested to see who's here on the chat. Looks like from our statistics, we have 5 or 10 people. There's Andy. Welcome, Andy. Good evening. So tonight, what we're going to do is we're going to look at the activity series of the metals, because this always comes up on exams. And it's related to redox, which we've been doing the other evenings, in that all single displacement reactions, which we use the activity series for, they're all redox reactions too. Hey, there's Caleb, who asked about tritium, T6. Wow, a lot of folks are here. Ara, excellent. So yeah, we're going to do activity series tonight. I've got 2 demos for you, which are kind of fun. We did one before, but I think it'll be a little clearer tonight when we do it. So let's get started on this. Let me jump over here. Here we go. There we are. So I have 7 different problems we're going to work through, try to do some demos, and really understand this activity series thing. So let's start out with the first one. Here it is. So you can use the activity series, called the activity series of the metal. You can do that and use it to tell which metals are going to be more reactive in single displacement reactions. Hey, Francesco, thank you. Appreciate it. So give this a try. Look at the activity series here. I'm going to make this bigger for you. And see which ones of these pairs are going to be more reactive. Let's see. So it's actually pretty easy, right? Because you look at the chart, whatever's higher up is more reactive. So if we're looking at copper and iron, right here's iron, right here's copper. Iron's going to be more active. If we looked at the sodium here, make my pen a little bigger. There we go. Sodium is a very active metal. If you put sodium with other stuff, it will react quickly. And silver's way down here. So sodium's going to be very active. And then gold, Au, right at the bottom. And that's kind of interesting because silver's not very reactive, but gold is less reactive. And that's why we have it in jewelry and all these other things. It doesn't react with things, so it stays nice and pretty. So that's how, so we're saying that silver is more reactive because it's higher up. That's how you use this activity series of the metals to figure out which is going to be more active. So let's take a look and see how that kind of transpires here. All right. So what we have is solid copper metal here. It's just copper wire wound up. And so here's the copper. And then they put silver nitrate. It's aqueous. It's a solution. So they pour it in here. And what's really crazy is that because the copper is, the silver is going to actually, we want to see which one of these reacts. I'm getting confused. We want to see which reaction is going to happen. So we start with solid copper. We end with solid silver. So you could just look at the reaction, right, and tell which one is going to happen. So think about that for a second. So here's our evidence. So we could use the activity series too. We could find copper and silver. So it looks like copper is above silver. So copper can actually push the silver out. But silver, because it's not as active, it cannot push the copper out. So this cannot happen. This is the only reaction that can happen. So that's why the silver right here, that's what you're seeing. These shiny things are silver. And then the blue color, that would be the copper 2+ here, this ion right here. So very useful, this activity series. All right, let's see what we got down here. So who else is here? I feel like a lot of folks that are usually around, I do not see. Jason, you out there? Jason's almost always there. All right. So now you give this one a try. see which one takes place, and then we'll actually do the demonstration. I really like this demonstration too. So I'll get my chemicals ready while you do that. All right, so when we look at this, right, we can look at the activity series. We can look at iron and copper, and these are single displacement reactions. Here's iron and copper. So we want to know if the copper can push the iron out or the iron can push the copper out. And it looks like the iron is up higher. So we kind of think this is what's going to happen. So let me jump over to my beaker here. Is there my beaker? It's close to it. Put some more light on this. So what I have is a pair of pliers, and they're kind of like shiny metal pliers right here. And I'm going to put some of this blue liquid on it, which is copper 2 sulfate. So if we're right, we should see from the blue liquid actual copper come out, and we should have actually like copper right on the iron. Some of the iron, that should go into the solution. It should dissolve. And you might even see that right now. You see the kind of copper color stuff around the edge starting to form in there. We'll let that go for a second. So Andy, you were right. That's what's going to happen. We should get solid copper in the product. And that's because the iron's so active, it can just push that copper out. All right, so if we leave this, you'll also see the blue color is going away. Look at the blue color is just kind of going away from the sides as that copper is being deposited on there. So if you wait longer, all the blue will be gone. But let's wipe it off and see what it looks like now. And now you can see that is the copper. That is actually copper metal, and it will stay on there as well too. I could actually make my pliers all copper by dipping this in a solution of this copper 2 sulfate. It's not electroplating, but because it's redox, electrons are being transferred around from the iron to the copper, right? So the copper is solid. So anyways, I really like that. I'm going to put some more on here, and then we'll come back to it and see what they look like. Let's kind of coat it here. See if I can make my pliers copper. And they're a little dirty, so it's not quite perfect. I didn't have a big sheet of iron to work with. All right, we'll leave that on there. See what we get. Let us go back here. All right, so that's the first demo. I'm going to turn this light off too. I have this other light here, and it is blinding. I think I'm going to lose my vision from it. All right, so we said that we're going to end up with this equation right here because we saw the copper. So we know that that's the equation, and that's how they came up with the activity series. They just put a bunch of stuff together and saw which was more active and made a list. That's it. All right, let's give you another one here. So this is kind of something, if you just think about it for a second, why is it more active than copper? What is the underlying reason? Hey, the Mozart 79, welcome. So think about that question. Why is iron more active than copper? Hey, thank you, KS. I'm glad that helped clear up some of the concept. And seeing it happen too is also one of those things that always helps me understand as a learner, is to actually see the reaction take place. So if you look at why iron is up here higher up than copper, It does have to do with the atomic radii. That's one of the things. And you can see that if the atom is bigger, what ends up happening is that the electrons are further from the nucleus and you can pull them off easier. That's a reaction. Pull them off and have them react. So iron is a little bigger, so atomic radii. Electron configuration is another thing that plays into it. Copper is one of those exceptional electron configurations. Essentially, it has its 3D orbital half full, so it's more stable. So that does play into it. Since copper is more stable, doesn't react as much. But also ionization energy, how easy it is to remove electrons, which is related to these other things, and then electronegativity too. So all of these things right here play into it. But the point is as a scientist, a chemist, or a student, when you start asking these questions here and really thinking about them, you start tying concepts together, and that's where the real deep learning takes place. So that's where the real growth takes place. But you got to work hard to get to this point. And I think most of y'all are all well on your way. All right, let's go down here and give you another one. And then we'll do this demo again. I think I have a better setup this time. Which reaction takes place? And you can use the activity series. All right, so let's actually do the reaction, and then we can see which takes place, and then we can relate it back. That way you'll really remember it. All right, so we have aluminum, our aluminum here, and our copper 2 sulfate. That's one thing we could start with, or aluminum sulfate and copper. I'm going to start with aluminum, see if the reaction happens. Let's go over to our beaker. But we'll see, David, what happens there. So if it's number 2, we should see actual copper metal showing up. Let me move this. So I've taken a watch glass, this right here, this watch glass, you can kind of see it here, and I've covered it in aluminum foil. So what we're going to do is dump a bunch of copper sulfate right in our little watch glass covered in aluminum foil. So if Caleb and David are right, we should see copper forming. And I actually have to go get another ingredient, because what happens is this reaction will happen, but it's very slow. If I put a little bit of table salt in, it creates holes in the kind of coating on the aluminum foil, and it happens quicker. So I'm going to run and get some salt. I will be back in a second. All right, I got it. Here we go. So I have my just normal table salt here. I'm going to sprinkle some of it in here. It's kind of like a catalyst. It doesn't react, but it gets the reaction started. It punches holes in the little coating on the aluminum foil. Get it dissolved in there. All right. If you're looking, I can just start to see just a little bit forming in there. Put some more copper 2 sulfate in. That's always a good idea. It's kind of slow to start tonight, but I see it actually right now, right here. This part right here where my pen is, now that my pen has copper sulfate on it, is starting to really start to change. We're starting to see that copper there. And you will see some bubbles form. The aluminum, when it's exposing, right, it's actually causes the aluminum to react with the actual water. Aluminum will react with water too. Now can you see it? Can you see the dark area forming up here? That dark area is solid copper. So why don't we leave the solid copper there to sit, and we'll come back in like a minute or two and check. But you can see how quickly this is happening. I don't know why teachers don't do this experiment more, because copper 2 sulfate, it's really safe, right? And aluminum foil you just have, so you could do this in class easily. But my students always love doing it. So how would adding heat affect the reaction? I think it would speed it up a little bit. That usually does speed reactions up, but I don't think it's such a quick reaction that I'm not sure it would make a big difference, but it would make some. And thank you, David. All right, so how about we do this? We go back and look at this, and then we'll come back to our reaction in a minute. You'll be surprised how much it changes. All right. So can we agree that the stuff we're seeing, that dark stuff, is copper, so it has to be this one here. And if we look at aluminum right here and copper way down here, aluminum is more active. So aluminum should be able to push the copper out in that single displacement reaction, and we should get solid copper. Whoa, what happened there? We should get solid copper. That's single displacement. No, I don't know if I would use a lighter in my house here, David. I'm at home. I'm not in a lab right now. Although in a lab, yeah, I would have the Bunsen burner out to be certain. All right. So this is a trick question. Oh, actually, I'm going to go over to the beaker because it's acting a little bit. If you guys can hear that, you can see the bubbling. So there's two chemical reactions actually going on now. Aluminum reacting with water, and then the copper 2 sulfate reacting with the aluminum. And it's already eaten a hole. Right here, there's already a hole in the aluminum foil. It's gone. It ate all the aluminum foil up. And this metal here that I'm moving around, that is solid copper. It's not shiny, but if I heated it up, I could make a little droplet of copper, make a penny or something. So yeah, it's just chewing it up. In fact, the blue color is gone almost, which means we got to add more. Let's add some more in here. Make it blue. So when the blue's gone, all the copper 2 is gone. All right, back to our trick question. Here's the trick question. Which reaction happens? If you see the trick, you can put it in chat so other people can see. I'll give you a hint. I didn't give you the activity series here to help you out, because the activity series is not going to help you out much here. No one sees it yet? All right. So here's the problem. When we're doing double displacement, when we're doing activity series, it only works on single displacement. But this is a double displacement, because you have sodium and copper, but then each of them are attached to a polyatomic ion. So the only way you can figure this out is by looking which one of these is going to produce a solid. So these are aqueous. I would say that according to the activity series, Andy, that sodium's reactive, but in this case, since this is a double displacement reaction, we can't use the activity series. What we're looking for is which one of these here, what is a solid? LID, I can do it. Which one of these over here is going to be a solid? And when we find the one that's a solid, that's the thing that caused the reaction. So what you need to do is look at solubility. So this is a double displacement. Knowing your types of reactions, then that's the way the teachers will try to trick you. give you a different reactions. With single displacement, you use activity series. With double, you use solubility. So Cu, copper, OH, hydroxide. We go over and insoluble. That means this is a solid. Sodium here, where's sodium? Right down, way down here. Sodium and sulfate, that's S, that's soluble, so that's aqueous. So we can tell already that, we have a mess here. We can tell already that this reaction is going to happen because we're going to get a solid. Both of these, if you look them up, aqueous and copper sulfate, they stay dissolved, so nothing would happen. So you can tell the reaction that produces a precipitate, that's the one we're looking at. We should do that reaction. What do I need to do that? Do I have that? I think I have those chemicals here. Let me grab the chemicals. Yeah, let's do this real quick. So I've got to wear, for this one, the sodium hydroxide is a little bit on the dangerous side. So I have to wear some protection here. But let's do it. Let's go over to our beaker. Now I sound like I'm in a tunnel. Right here is our beaker. I want to move our other stuff around a little bit. All right, so what I'll do is I'll take and put some sodium hydroxide, which is a very strong base. It's a clear liquid, but it'll hurt you. And I'll put some of it in here like this, and then we'll put our copper 2 sulfate in. I keep hitting the mic. Here we go. All right. So watch what happens when we put the copper 2 sulfate in. That's where we should get that precipitate we were talking about, the copper 2 hydroxide. So this is a kind of a almost clear, little bit blue liquid. Nothing is happening. Makes me wonder if I have the right solution. That's disconcerting. Let me grab the other one. Well, unfortunately, nothing happened, which makes me think that I have the wrong solution. So we will have to do that demonstration another evening, which is unfortunate. Let's just go back and look at where we were here, though, and finish up with this reaction here and show you that. Just look at how the copper here just destroyed the aluminum foil, just ate a huge hole in our aluminum foil. That was our single displacement reaction. Started with aluminum metal, got copper metal. All right. Go over here. Yeah, I know, Caleb. I was kind of excited. I don't know what happened there. I'm going to have to think about that for a little bit. That's a pretty reliable reaction. I probably have the wrong chemical. All right. Well, let's do one last one here because we're getting to time. How about this? The last thing that you'll see teachers give you on an exam with activity series is you can actually use the activity series for what are called the halogens on the periodic table. So the halogens on the periodic table, they're the fluorine, chlorine, bromine, group 17. Those are the halogens. And we can tell their reactivity using the activity series for the halogens. So they're not metals, they're non-metals. So see if you can figure out which reaction happens here. Can chlorine push out the bromine, or can bromine push out the chlorine? So use this here to help you figure that out. All right. So fluorine is up here above. We're looking at chlorine and bromine, so we don't care about fluorine. Here's bromine and here's chlorine. So chlorine is more active, and hey Lobster, good to see you. Since chlorine is more active than bromine, it can actually push the bromine out. So the bromine's by itself. So Andy, you're right, you got it. And because chlorine is higher, right? So yeah, so the chlorine is up higher, so it can actually push the bromine out. It's so active that it pushes it out, and we end up with bromine by itself. It's still a single displacement reaction. It would still be a redox. But so this is just a little bit, sometimes they'll give you this as well. And just know as you go up, fluorine is more reactive than chlorine, chlorine's more reactive than bromine. And this has to do more with atomic radii because fluorine's really small and we get bigger as we go down. But electron configuration a little bit too. So that is it. One last thing, I do want to check and see if I go over to my beaker again, the solution that I was using, is it sodium hydroxide? And the way I can test that is I can put some pH paper in here. So I have my pH paper, and I don't know what this solution is. I think it's magnesium sulfate. It's definitely not a base. It's not sodium hydroxide. So I need to label stuff better. All right. I think that's going to be it for me tonight. I'm getting a little tired out. Thank you everybody for coming, and everybody that is signed up to help out with the oxidation and redox guide. Thank you very much. I look forward to your responses. And David, we'll be back on Tuesday, and I'll get the right chemicals so we can actually see that happen, because that is that's one of my favorite reactions. So thanks a lot, everybody. I'll stick around in the chat for a few more minutes, and if you have questions or anything, but I'm going to end the stream, and I will see you on Tuesday. Yeah. This is Dr. B, and as always, thanks for watching. Oh, I haven't ended the stream yet. There we go. End.